whenever you're ready.
Yeah, for sure. Yeah.
Okay, great. Welcome back, everyone. So it's great to have David Woodruff here. David is one of the long-term participants and also one of the main organizers of the previous workshop. So it's great that he's agreed to give us talk in this workshop as well.
Okay, yeah. Thanks for inviting me, and thanks for coming. So the title of the talk is Tight Bounds for Active LP Regression and Beyond. This is based on two different works. The first is joint with Cameron Musco, who's here, Chris Musco, and my student Tai Yasuda. And the second is a follow-up with Tai Yasuda. So yeah, let me tell you about the active learning setting that we consider. So here is a standard problem in active learning, an example. So here is a chest CT scan of a patient, say. Think of this as a data point. And you want to know, does this patient have COVID or not? So you go to a doctor, and the doctor looks at this example and says, that lung definitely has COVID. And then he says, that'll be $50. Okay, so this is a label that we're assigning to this example, which is expensive. Okay, and in general, the idea behind active learning is that oftentimes the largest bottleneck in machine learning applications is the collection of labels. Okay, they don't need to be necessarily costly. It could be that you need to feed an input through a very complicated model just to get the corresponding label. And so active learning aims to minimize the number of label entries that are read. Okay. And the most basic question in active learning, or one of the most basic, is active linear regression, which is what we're going to focus on in this talk. Okay, so here's the problem setting. This is the standard vector p-norm. What are we given? We're given a design matrix A, which is n by d. Think of the rows as being n examples. They each have d features, which is also the number of variables that will be in the regression problem. We'll consider the over-constrained case, so we're thinking of many more examples n than features d. And our access to the label vector b is through query access, okay? We want to minimize the number of queries to this vector b. And what do we want to output? We want to output a coefficient vector x prime and r to the d. And we're looking for a relative error solution here. So the p-norm of ax prime minus b, the regression cost, is at most 1 plus epsilon times the optimal regression cost. Okay. And as I said, we want to minimize the number of entries in B that we read. Okay, so what is known about active LP regression? Using classical techniques in randomized linear algebra, it's not hard to get, for least squares regression, p equals 2, it's not hard to get a bound of d log d plus d over epsilon. You can show that just sampling according to the leverage scores of a matrix gives this bound. So the leverage scores of the A matrix, it doesn't involve B at all. And so that's what you can get with standard techniques. A result of Chen and Price was able to get rid of this log d factor, so they get a tight query complexity bound of d over epsilon. Okay, and their proof uses BSS-like techniques. It's a randomized algorithm, of course, as all algorithms need to be in the active setting. Then came a work of Chen and Derazinski, and independently of Perlikar, and Price, which studied p equals 1. Now, unlike p equals 2, which has a lot of algebraic structure, you can kind of take the objective function, use Pythagorean theorem to decompose it into a part only depending on A, and a part that is a dot product for which you can sample from A and approximate the dot product with B. Has nice algebraic structure. P equals 1 has less algebraic structure, but it still has nice structure. Okay, so using specific properties of p equals 1, those authors were able to show a tight bound of d over epsilon squared up to log factors. Okay. And they kind of, they use a really nice form of looking at the difference of, they look at quantities of the form ax minus b1 minus ax star minus b1. And this can be upper bounded in terms of just the norm of ax minus ax star, the one norm. So when p equals 1, there's a very nice way of controlling this quantity. And so they were only able to get a result for p equals 1. That's kind of what I'm trying to say. They did do some kind of Taylor expansion on a related quantity to get some bounds for p between 1 and 2. They were able to get a worse d squared over epsilon squared bound. And one of their open questions was, can you get linear in d? And what is the optimal epsilon dependence for p in this range? Okay, so this is the state of the art before our work for LP regression, active LP regression. Okay, so in our work with Musco, and Tai, what we first were able to show is that for p between 1 and 2, that you can actually get a d over epsilon bound. Okay, so you can improve this d squared to d, and you can improve this epsilon squared to epsilon. And that's also tight. Okay. For p greater than 2, in our initial paper, we had a bound, we had the first non-trivial bound for this range of p. We had a bound which was d to the p over 2 over epsilon to the p. This was an upper bound. And we had a lower bound of d to the p over 2 plus 1 over epsilon to the p minus 1. So this is what we had in the first paper. And in the follow-up paper, we were able to get a tight bound, which is d to the p over 2 over epsilon to the p minus 1. Okay. And I'm not going to talk much about it, but when p is less than 1, it's not a norm, but you can still think of the LP norm as a well-defined quantity, and you can get tight bounds of d over epsilon squared in that case. We show that. Okay, so it's active LP regression.
Sorry, David, quick question.
Yeah.
So is p also 1 over p equals 1 also 1 over epsilon, or is it 1 over epsilon squared?
No, so this is very interesting. So when p is 1, these papers show that d over epsilon squared is tight. They provide a lower bound. And once p is slightly larger than 1, so we're assuming here p is a constant between 1 and 2, then the bound becomes d over epsilon, because there's a phase transition at p equals 1. Okay.
So if you sort of parameterized it, there would be some funky...
Oh, function of p. Is that as it approaches 1?
Like say if p was a function of d, then there would be some weird extra dependence somewhere, like as p gets very close to 1.
Yeah, as p gets very close to 1. Yeah, exactly. Yeah. I'm assuming here that p is a constant bounded away from 1. Any other questions? Okay. Okay, so I just mentioned the results for LP losses. I'm just repeating them here. I've drawn the least squares loss and the L1 loss. These were the bounds that I said. In the paper, we also get bounds for a large number of other loss functions of M estimator losses. And in particular, we look at one of the losses is the Huber loss. So the Huber loss is quadratic near the origin, and at some point it shifts to becoming linear. And this is useful. It enjoys smoothness properties near the origin and robustness properties away from the origin, like L1 loss also enjoys, but L1 loss is not smooth. And for Huber loss, we get kind of a weird looking bound of roughly d to the 1.172 over poly epsilon. We also consider Tukey loss, another popular M estimator, which is quadratic near the origin, and at some point it just becomes completely flat. Okay, and for this we get d squared over poly epsilon, and I'm hiding log factors. And we handle many other M estimators. we're not getting tight bounds in terms of D. There's some very recent work of Aaron Young, Aaron, and James Lee that gets, I believe, subspace embeddings for Huber loss and Tukey loss. I don't know if they apply to the active setting. So, yeah. Probably. Okay. Yeah. Okay. So that would be great if that works. Then for the active setting, the hope is that you can get D over poly epsilon. Okay. So yeah, and I just want to motivate one more simple application of active regression, which is Kronecker product regression. This is a problem that is well studied in signal processing communities and some other places where the design matrix is only given to you implicitly. Okay, so the design matrix is actually a Kronecker product of Q matrices, A1 through AQ, that you're given. So here, think of each AI as being n by d, n much larger than d. And so this actual matrix, this Kronecker product, is n to the q by d to the q. And maybe d to the q is tolerable, maybe d is not so large, but maybe n to the q is way too large to do anything with. And you'd like to solve this problem. So and maybe you're not you're not in the active setting. You could read B. It's not expensive to read B, but B is an n to the q dimensional vector, so it would take a lot of time to read all of it. Yeah, so as I said, this is used in signal processing. It's also used in spline regression. And there's previous work on this problem. The best previous work obtained 1 plus epsilon approximation in the number of non-zero entries of the AI, the sum of that over I, but it had a plus n and z of B term. Okay, and as I just said, that's really bad, right? Because n and z of B can be as large as n to the q if you have a dense label vector. So the hope is that you could remove it, and using these active regression techniques, for every p, we can remove this n and z of B term and get a real input sparsity time algorithm for Kronecker product regression. Okay, this is a simple application. Any questions? Okay, so let me give a proof sketch of the bounds for LP regression, and if time permits, talk a little bit about M estimators. So here's the plan for the proof. In the first part, I'm going to discuss sensitivity sampling and more refined notions of that called chaining, and a key idea that we use, which is partitioning the label vector by sensitivities. This first part will allow us to obtain optimal dependencies on D for LP regression, for every P. And then I'll talk about the second part, which I'm calling iterating with near optimal solutions. I'll describe what that means, but this will allow us to get optimal dependencies on epsilon as well. Okay, so here's the high-level algorithmic approach. The idea is to try to select some important training examples. It's just rows of the design matrix A, and read the corresponding labels of the label vector B, and possibly, or usually you want to reweight what you've read and solve the smaller problem. Okay, this is the algorithm that we would like to work. So we'd like to design some distribution to choose important examples. What does important mean here? Okay, so that's sort of a sample and solve approach. And so let S times A be the sample and reweighted matrix, and S times B the same for the label vector. Well, sensitivity sampling gives you a natural way of choosing important training examples. Okay, so what is that? Well, what's one property we would like? We would like that S times A, this small subset of reweighted rows of A, we'd like it to approximate A in the sense that for all vectors that A acts on, for all x, we have that the p norm of SAX is within 1 plus or minus epsilon of the p norm of AX. Okay, so how should we sample rows of A with no particular x in mind? We'd like this to hold for all x. Well, sampling each row proportional to its sensitivity can get this. What is the sensitivity? So the ith sensitivity of A is the supremum over x of the ith row of A dot x, absolute value to the p, over the p norm of ax to the p. Okay, so it's the supremum as I range over all vectors ax in the column span of A of the fraction of the p norm that's in the ith entry, or fraction of p norm to the p in the ith entry. Okay, so that's the ith sensitivity. What's important is the ratio of these two quantities. And the sensitivity score, as I said, captures the largest fraction of LP norm by the ith coordinate as you range over the subspace. There are nice properties about sensitivities. So the sum of the sensitivities is not too large in the sense that it doesn't depend on n. So if p is less than or equal to 2, the sum is at most d. And for p larger than 2, it's at most d to the p over 2. Okay. Yeah, if you haven't seen these before, when p equals 2, the sensitivities are actually the squared row norms of an orthonormal basis for the column span of A. And the sum of the squared row norms is the same as the sum of the squared column norms, and that's why it's equal to d in that case. Right? The sum of squared row norms of an orthonormal basis is d. So that's sort of the proof for p equals 2. And this is the generalization to arbitrary p. So I'd just like to stress here that what this sum says is that not too many rows can be too important. Okay, it's small. Now, one problem with sensitivity sampling in the active setting is that this label vector B is not a column of A. And sensitivities of A do not necessarily capture large entries of B. There could be some very large entry of B that's attached to a row of A that has very small sensitivity.
Sorry, David.
Yeah.
I'm going to ask another question.
Yeah.
When you said that your results for p greater than 2 are typed,
yeah,
this is related to like this quantity is also typed or something. The one you just showed, this the large leverage score sum.
Yeah,
for
I'm actually going to. I'll actually give you a lower bound for active regression for So the type bound was theta d to the p over 2 over epsilon to the p minus 1. And you can show a hard instance where if you don't read this number of entries in the B vector, then you can't get a 1 plus epsilon approximation. I mean, it is related to that because ultimately there's an algorithm that uses facts like this to achieve this, but the proof is just a direct hard instance. Yeah, yeah. Any other questions? Okay. Yeah. So the point here is that B is not a column of A. So the distribution that you're looking at doesn't capture large entries of B. So what can we at least get very easily? Well, we can start by getting a constant factor solution without looking at B at all. So if we sample, here's how you do it. If you sample each row of A with probability equal to its sensitivity, then what you can show is that for a fixed vector x, the p norm of SAX is within a constant factor of the p norm of AX with constant probability. Okay, this is just an expectation, a second moment method argument. Okay. And what is the expected number of samples that you take? Well, for each row, if you're including it with probability proportional to its sensitivity, then the expected number of samples is the sum of the sensitivities, which we said is fairly small. Okay, so this was for a fixed x. How do we get a statement for all x? Well, you can show that the dependence on the failure probability will be log 1 over delta. So you'll get log 1 over delta times the sum of sensitivities bound. And if you just do a standard net argument, you choose an exponential and d-sized net, then you can union bound over all net vectors. So Bernstein's inequality plus this net argument will give you d to the max of 1 in p over 2 plus 1 rows. And now you can say the statement that for all x simultaneously, the p-norm of SAX is within a constant factor of AX. Okay, why is this useful for active regression? Well, let's just say that we do this sensitivity sampling with this number of rows, and we get our matrix SA and corresponding label vector, part of the label vector that we read, SB. And we do this sample and solve approach. So we solve this small problem, and we get our constant factor solution. Let's call that x sub c. Why is this a good solution? Well, it's a very simple argument based on triangle inequality. If I look at the cost of using this solution, xc, then the LP regression cost is by triangle inequality, at most the LP regression cost of AX star minus B, where X star is the optimal p-norm solution to the regression problem, plus the p-norm of AX star minus AXC. That's just triangle inequality. The next inequality, this optimum AX star minus B p-norm is the same. And all we did is we said that this quantity here is at most S times that quantity, right? Because S is a constant factor subspace embedding. Yeah.
So I've never used norms between 0 and 1. They're not norms, but this doesn't hold for between 0 and 1.
Yeah, you can get an approximate triangle inequality. You lose something there. Yeah, yeah. Any other questions? Okay. So we need S, to not shrink the norm of any vector, and that's what this property says. What do we know about this p-norm? Well, we can again apply a triangle inequality and say that the p-norm of SAX star minus SAXC is order, is the p-norm of SAX star minus SB plus the p-norm of SAXC minus SB. Right, that's just triangle inequality again. I just put a B for both of these. Finally, what do we know about this sum? Well, XC is the optimal solution to the sampled problem, right? So that means that this p-norm is at most this p-norm, right? Where X star is the optimal solution to the original problem. Yeah. Okay, so we just need to understand what is the p-norm of SAX star minus SB. And the sampling matrix S gives you an unbiased estimator for any fixed vector X star. That doesn't depend on it. It's just some fixed vector X star. And so it's a non-negative random variable. Just by Markov's inequality, this is at most a constant factor times the p-norm of AX star minus B. And that's order opt. Okay, so this is a very simple way to get a constant factor solution to active regression just by sensitivity sampling. Okay, the number of rows you get by doing this is not tight. You can get rid of this +1 using more sophisticated arguments. But I just wanted to give you an initial, I'll talk about those a little bit later, initial bound. Okay, so how can we get a 1 plus epsilon approximation, though? Okay, so let me first mention some simplifications. So we can first get an order 1 approximation, x of c, as we just described. And we can conceptually, or even algorithmically, replace b with b minus a times xc. Okay, we don't actually have to do the subtraction, but every time we read an entry of b, we could replace it with this. You don't have to do this. I mean, in the analysis, you should think of b being replaced with b minus axc. Why is this useful? Well, now you see that the norm of b is of the new b is order opt. Okay, which means by triangle inequality, you only need to consider those x for which the p-norm of ax is order the norm of b. There's no reason to consider larger x because by triangle inequality, they'd have a cost that's larger than order norm of b, which is order opt. Okay, and by linearity, let's just assume that the optimal cost is 1 for the talk. And so just to summarize, the p-norm of AX is order the p-norm of B, which is order 1. Okay. So let me describe now the main idea for getting this optimal dependence on D. The main idea is that labels in the B vector that are too large are not important. Okay, if I have some very large entry in B, and it's attached to some very small sensitivity in A, then if I really try to fit that entry in B, then, since the sensitivity is so small, I have to set the norm of AX to be very large. And if the norm of AX is very large, relative to opt, then it means that, I'm already not getting a constant factor solution, much less a 1 plus epsilon approximation. So the idea is I can't actually fit entries of B that are very large. Okay, so labels that are too large are not important. So let me just draw the picture here. Okay, so again, from the last slide, we said that the p-norm of AX, we're going to assume is order 1. So that means that if I look at the ith coordinate, the largest that ai.x to the p could ever be is the sensitivity, sigma I. Right? It can't be larger than that if the p-norm of AX is order 1. Okay. Well, now let's look at coordinates of B. So if I look at a coordinate of B, there's sort of two cases. One is it's not too large. And by too large, I mean it's not larger than sigma I over epsilon to the p. This turns out to be the right threshold to look at. So if it's not too large, then you can think of BI as being comparable to the ith sensitivity. And so then when you try to go through the analysis using AX minus B, the sensitivity analysis or more sophisticated chaining analyses, then you can kind of, it doesn't change that much because the coordinates, these coordinates of B are very comparable to the sensitivities. They don't change the sensitivities of A. So that's the good case. And the bad case is when you have some coordinates that are very large. Okay, and this can certainly happen. Some coordinates could be infinite. You'll never read them. You don't know about them. Or you could, with some probability, read them, but you're not going to try to fit them. That's the point. Okay, so if I have a very large coordinate BI, then AX minus B, the ith coordinate, is dominated by BI for every x that you care about. For every x such that the p-norm of AX is order 1. Okay, and what that effectively means is these are not going to affect the cost, and they can be ignored. Okay, you need to formally show this, and I'll say a little bit more about that. But that's the high-level strategy of the proof. So yeah, let me describe where we are. So sensitivity sampling selects important rows of A. And the problem is that this preserves the LP norm objective for AX, but not for AX minus B. And this idea of partitioning coordinates of B by sensitivity, it effectively allows us to ignore large entries of B. Okay, so if BI is much larger than sigma I, I'm dropping epsilon factors, then it cannot affect near optimal solutions. Okay, you can show that both after sampling and in the original for the original regression problem. And so for the purposes of analysis, we can actually zero out such BI, obtaining a vector B prime, where all the entries in B prime, they're either 0 or they're at most this place where we cap the entries, this sensitivity divided by epsilon to the p. And you can show that the sensitivity sampling argument on B prime goes through. Okay, so that's the rough idea. One issue with this is it's using sensitivity sampling, so it's already not going to get optimal bounds. It ends up getting d to the p over 2 plus 1 instead of d to the p over 2. But it actually, it does go through. To get better bounds, we use chaining arguments with Lewis weights. Using chaining arguments goes back to Bourgain, Lindenstrass, and Millman, and Ledoux-Talleyrand simplified their proof. Using such arguments, we're able to improve the bounds to d to the max of 1 over 1 and p over 2. So it's optimal dependence on d, and some dependence on epsilon, which is suboptimal. What are Lewis weights, if you haven't seen them? So the LP Lewis weights, which I've written as W1P, W2P, WNP, they satisfy a very nice equation defined in terms of themselves, which is that the ith Lewis weight is the L2 sensitivity, which is just the leverage score. I didn't define leverage score, but it's the L2 sensitivity of W to the 1/2 minus 1 over P times A, where W is a diagonal matrix, which has the Lewis weights, the LP Lewis weights on the diagonal. Okay, so a priori, it's not even clear that such Lewis weights exist, but they do. They can be found efficiently. There are algorithms of Cohen, Peng, and others that find these very quickly, find good estimates of these. And you can, compute these to high accuracy and so on. So there's a lot of study on Lewis weights. They can be found quickly. And they're related to sensitivities. There are nice relationships. So the ith sensitivity, I'm writing it here as SIP, but it's still the same sensitivity that we had before. The ith sensitivity with respect to the p-norm is at most d to the max p over 2 minus 1 and 0 times the ith Lewis weight. Okay, so when p is less than 2, the Lewis weights upper bound the sensitivities. Otherwise, there's some poly d loss. Now, how do we use this in the active setting? We initially had a proof that went through Bourgain, Lindenstrauss, Millman. It was very messy. But there's a much simpler proof due to Ledoux and Talleyrand, which we end up using. We end up using that because it changes very minimally in the active setting. Okay, when you have this vector B prime. So let me just say what the algorithm that we analyze ends up being, which is the algorithm, well, it's existential in the Talleyrand, but this is the sort of the algorithm from there. So here's algorithm 1, which I'm calling LP sampling. We have the matrix A as input, and we want to output a diagonal sampling matrix S. How does it work? Well, we first compute approximate Lewis weights. So this Lewis weights W tilde I are overestimates to the actual Lewis weights. And instead of summing up to at most D, they sum up to something that's slightly larger than D, C1 times D. Then we take this matrix A, and we need to flatten rows of A. What does that mean? We're going to create a new matrix A prime by replacing each row in A with some number of copies of it. Okay, so for the ith row, we replace it with k copies, where k is proportional to the Lewis weight, the ith Lewis weight of A. So it's the Lewis weight of A divided by roughly d over n. And for each copy, we scale it by k to the 1 over p, 1 over k to the 1 over p. If you do this, then the LP norm is preserved for any x. A prime x p norm is the same as ax p norm for any x. And the nice thing about doing this is that the Lewis weights of the new matrix A prime are all flat. Okay. And so what do you do now? Well, now in A prime, you independently sample each row with probability 1/2. Okay. And for rows you sample, you scale back up by 2 to the 1 over p. This will preserve the p norm in expectation for a fixed x. If you set the constants appropriately, the number of rows in A goes down by a constant factor. Okay, you need to set this C2 to be large enough. This just influences the overall error in the chaining argument that you look at, and it can be accounted for by adjusting epsilon in other places. Okay, so the number of rows is going to go down by a constant factor. And so what is the recursive algorithm for LP regression? The idea is if the number n is small compared to the number of samples you want to make, then you just solve regression by reading all the labels in the B vector. Otherwise, n is large, and you just replace A with S times A by calling this algorithm, and replace B with S times B by calling this algorithm. You don't actually have to read the entries in B to do that. Okay, and so you just keep recursing until you get down to the number of rows that you want, which is the number of samples you're going to read. Okay, so each time you're reducing by a constant factor. That's the algorithm that we analyze. And just stepping back for a minute, like why are we looking at Lewis weights and analyzing this algorithm? Why not just use sensitivity sampling? I just wanted to give a little bit of intuition about that, if you're not familiar with chaining at all. So the naive sensitivity sampling analysis, as I said, you do a Bernstein argument and a net bound, and it loses a factor of d. The sample complexity is the total sensitivity times the net size. And the reason this is suboptimal is because it assumes a worst case variance. Okay, so after you split the coordinates and you have this matrix A prime, you can show that all the coordinate values are roughly within a factor of d that you care about. Okay, and sensitivity sampling, the analysis, it assumes that you're always going to get these slightly larger coordinates, these coordinates that are valued d instead of the flat coordinates. And that's why you lose a factor of d in the analysis. So instead, what chaining does is it has multiple nets, and it trades this high variance, this factor of d, for a smaller net size. Okay, so sort of the high variance coordinates can be covered, I'll say what that means a little bit on the next slide, with smaller nets. And so, even though you pay higher variance, the union bound is over a smaller number of things, and overall, you reduce the total sample complexity. So this is called compact rounding in the Bourgain, Linden, Strauss, Millman paper. And the goal is to construct a net n of vectors such that for any x, in the set you're trying to approximate, there's a net vector y that approximates ax on every coordinate up to a 1 plus epsilon factor. Okay, so you're trying to approximate this coordinate-wise, a vector ax, and you want your net of vectors to be small. And a key observation, which is called dual Sudakov minoration, is that the size of a covering of the LP ball ax by L infinity balls, you can imagine, you're trying to approximate this coordinate-wise, so you're trying to cover it with L infinity balls. If you look at L infinity balls of radius t, the size of the net that you need is exponential in d over t squared. Okay, I'm not going to prove this or give any intuition, but just the point is, when t is large, the net size is smaller, as you would expect, okay, because you have larger L infinity balls that you can use to cover vectors in your LP ball. And yeah, so the idea is to construct your net n using multiple L infinity nets with radii that are increasing in powers of 1 plus epsilon. And so this is sort of the rough idea behind chaining applied in the setting. That's all I'll say about that. Here's a glimpse of the analysis, the Ledoux-Talleyrand analysis that I was talking about. So the idea is to look at this quantity capital lambda. It's the supremum over vectors x such that the p-norm of ax is at most 1. We said we could look at those vectors because those are the only vectors that can give you 1 plus epsilon approximate solutions. And what we want to look at is the p-norm to the p of sax minus the p-norm to the p of ax. We want this supremum to be small. We want it to be at most epsilon. And this sampling matrix, well, it has this nice form that either I don't include a row, in which case I have a 0 on the diagonal entry, or I do include the row and I have a 2 when I raise it to the pth power, right? Because I'm sampling half and I'm scaling back up to preserve the p-norm. So I can write the diagonal elements of S as 1 plus sigma I, where sigma I is a Rademacher, a random sign. So I either, if I don't include the row, it's 0. If I include it, it's 2. And so, I just took this difference and wrote it coordinate-wise. And, taking differences coordinate-wise, I get the sum of sigma I times, absolute value of axi to the p. That's the quantity that I want to bound. So now I have this, if you've seen these, this is a nice Rademacher process. I can try to bound this, and there are known bounds on this quantity. So the bound of Ledoux-Talleyrand says that the expected value of this supremum lambda is something that looks like what we want. It's d to the max of 1 mp over 2 over n times some log factors, the square root of that. And so that's roughly what goes on in chaining without in the non-active setting, in the standard setting. And by the way, this expectation also comes with sub-Gaussian tail bounds. So Verschinen has a nice discussion of that. You get a sub-Gaussian concentration for this supremum. What I wanted to say about the active setting is things change a little bit, right? Because we have this b vector. We said that we can replace it with this vector b prime, where the max entries are capped by the corresponding sensitivities, more precisely by the Lewis weights that are related to the sensitivities in ways that I described. And so you kind of just push through the analysis with this extra b prime vector, and it works out. I mean, that's the short story of how this analysis works. Yeah, so putting that all together does give optimal bounds in terms of D for active regression for any P. Okay. Okay, in the remaining amount of time, I wanted to talk about the epsilon dependence. So a natural question is, can we do better? Those arguments I just described don't get the optimal epsilon dependence. Well, here's the idea, which I was calling iterating at the beginning of the talk. We can first obtain a 1 plus root epsilon approximation. Let's say we're looking at P between 1 and 2, okay? So we know the optimal number of queries is D over epsilon. That's what I was claiming to you. The previous analysis using chaining would have a 1 over epsilon squared dependence instead of a 1 over epsilon dependence. But it's still useful for getting an initial solution. We can first obtain a 1 plus root epsilon approximation with roughly D over epsilon queries using that analysis. Okay. Then the key point is that if I look at the LP squared loss, this is strongly convex with respect to the LP norm for P between 1 and 2. And so what does that, what does that mean? Well, what it means for us is that if I have a solution X such that the P norm of AX minus B is at most 1 plus gamma opt, then in fact, AX has to be close to AX star. Okay, you can't have AX and AX star being very far away and both having good solutions. And in particular, it means that the P norm of AX minus AX star is order root gamma times opt. Okay. But then, if AX and AX star are close, we can actually improve the chaining arguments. We can improve this framework that I was talking about. We get an improved bound. Like now we only have to look at vectors AX such that AX satisfy this. The P norm of AX minus AX star is order root gamma opt. Okay, this is better than what we were looking at before. Like in the old analysis, I was saying we look at vectors X first, the P norm of AX is order 1. That was order opt. And now we get this sort of smaller set that we have to look at. And because we have the smaller set, we can improve the chaining arguments. So if we improve the chaining arguments, then it actually means that with that same number of samples, you actually got a better approximation than you thought you got. And then you just keep iterating this argument, and you can iterate it down all the way to D over epsilon queries. So let me show that to you more precisely on the next slide. But before I do, let me just mention that, I can show you a picture of how this works here. So here is one of the LP loss functions, P between 1 and 2. And here is the optimum. We're minimizing, and here's the optimum at the origin. And we got some vector X for which the P norm of AX minus B is at most 1 plus gamma opt. So that means that, the value is below this dotted line. Okay, but then by strong convexity, it means that, okay, well, we only need to consider, it means AX is close to AX star. So we only need to consider AX in this range between these blue vertical lines. Okay, but then if we had AX minus AX star P norm in this range, it meant that we would have a better sampling bound. So actually, we would have had an even better, with the same number of samples, we would have had an even better bound on the cost. It would be below this yellow line. And then by strong convexity, that means that, actually, AX is closer to AX star than what we thought. And we just iterate this argument. And if you iterate it, you get down to, you can show that D over epsilon queries actually sufficed. Okay, so there might be a more direct way of proving this. This was our understanding of how to prove it. I do want to mention, before I formally mention the recurrence, is that this is also how we obtain the improvements for p greater than 2. Okay, I mentioned that we had this follow-up work that improved these bounds to this bound. We don't have this strong convexity, but instead what we use is a Bregman divergence of LP norms by people in this audience. Adil, Rasmus, Richard Peng, and Sushant. Using that bound, that Bregman divergence, what we're able to show is that if the P norm of AX minus B is at most 1 plus gamma opt, here P is greater than 2, then again, AX is close to AX star in P norm. Like the difference is order gamma to the 1 over P opt. Okay, so again, it's this idea that closeness in objective implies closeness in the actual vectors, and then therefore implies improved chaining. So, what is roughly the intuition of what's going on here? Let me just say something for P between 1 and 2. So, as I said, we have this simple lemma from strong convexity that if P is between 1 and 2, and the objective is of AX minus B is small, then AX and AX star are close. This was what was on the previous slide. So think of a case where AX minus AX star is a flat vector. Okay? All these differences are roughly the same. Now, suppose I wanted to uniformly sample entries to approximate the P norm. Right? So if I know, how many entries do I need to approximate the P norm of AX if I had AX star? Well, if AX star were equal to AX, I wouldn't have to sample anything. But if all the entries are very close to each other, then by uniformly sampling S entries, the additive error that I get is gamma to the P over 2 opt over root S. Okay, so it depends on how close these are to each other. Right? Intuitively, I don't need many samples if all the entries are very close to each other. And so if I want additive error epsilon opt, then we only need a number of samples S, which is, if you just plug it in here, gamma to the P over epsilon squared, rather than 1 over epsilon squared, which is what you would need in general, if gamma was a constant. So we improve. Yeah. So one thing I forgot to say is we can essentially reduce to this flat case by sensitivity and Lewis sampling and chaining. Okay. So these ideas of kind of flattening the vector that I talked about earlier kind of reduce to this case. Now, this is just intuition, but this is what's going on. Like you're looking at these Gaussian processes over differences of vectors, and this is why the error improves. Here is sort of the formal, slightly formal argument for P between 1 and 2. If a 1 plus epsilon approximation can be obtained by making D over epsilon to the beta queries, then a 1 plus epsilon approximation can be obtained by making D over epsilon to the 2 beta over 1 plus beta queries. Okay, it's saying that if you had enough samples to get this 1 plus epsilon approximation, then it meant that the solution vector you had is close to the optimal solution, which meant that you have an improved chaining, which means that you could have used this number of samples. So you see that if beta is 2, d over epsilon squared is enough to get 1 plus epsilon approximation. But then by this strong convexity, it meant that actually d over epsilon to the 4/3 was enough to get this 1 plus epsilon approximation. And if you just repeat this recurrence, starting with beta 1 equals 2, beta I plus 1 turns out to be 2 beta I over 1 plus beta I. I mean, is that? And if you work it out, beta I approaches 1, and we actually have an algorithm with order d over epsilon queries. Okay, so that's the idea behind this improved epsilon dependence. And the same kind of iterative argument works for p greater than 2. It's just the recurrence works out to something different. d to the p over 2 over epsilon to the p minus 1. Okay, so that's the idea how we get optimal epsilon dependence. Let me just say a few more things. So this bound for p greater than 2 might look somewhat arbitrary, but it's in fact tight. And here is a simple lower bound instance. So let's take our matrix A to have this number of rows. Okay. And what it's going to have is it's going to have d to the p over 2 distinct rows. And each row is going to be copied 1 over epsilon to the p minus 1 times. Okay. Now, what are these d to the p over 2 distinct rows? Think of them as all random unit vectors, independently random unit vectors. And so morally, you should think that every pair of dot products between them is at most order 1 over root d. Okay, there's a log factor, a root log factor there. There's actually an explicit construction that avoids that log factor. I don't care about log factors right now. Okay, so that's your input matrix A. It's clear? Right? D to the p over 2 random vectors, and then copy each of those 1 over epsilon to the p minus 1 time. Okay, so what is the B vector, the label vector? Well, in one case, it's 0. And the other case is the random standard unit vector, EI. Okay, so it's 1 in one coordinate, 0 everywhere else. If you want to figure out which of the two cases you're in, you basically have to read all of B. Okay, so B has the same size of A. It's d to the p over 2 over epsilon to the p minus 1. Why do you need to read all of B for the error guarantee that we care about? Well, if B is 0, then we have to output x equals 0. Right? We want a relative error solution. Right? The cost is actually 0 if B is 0. So we should output x equals 0. But what happens if B equals EI? Well, if the algorithm outputs 0, it just pays the norm of B, which is 1. But there's a better solution. Instead, what you should do is you should have your unknown x vector be the ith row of A, where I is that standard unit vector, right? It should be the ith row of A times epsilon. If you do that and work out what the cost is, you'll get that the cost is actually at most 1 minus theta epsilon. Okay, you save a little bit by fitting that ith entry. And the sort of total cost from all other entries is small enough that overall you get 1 minus theta epsilon. Okay, I don't want to do the calculation, but that's the idea. Questions? Okay. Yeah, so I'm almost out of time. I'm going to skip the extension to M estimators, but let me just say that for a large class of M estimators, we do solve active regression with roughly d squared queries. And for some M estimators like Huber that I mentioned, we optimize it further to get close to d, but not actually d. One of the key ideas that goes into this is bounding the sum of sensitivities for an arbitrary M estimator. And we use a hashing technique to reduce the we use a hashing technique to argue that, so what does hashing technique mean? We have our matrix A, we randomly split it into a small number of matrices, and we compute L2 leverage scores on that small number of matrices. And these L2 leverage scores turn out to capture the sensitivities. So I guess I won't get into it, but the idea is to somehow relate sensitivities to leverage scores by breaking up the matrix into random pieces. Let me just say that. Okay, so I'll just conclude then. Yeah, there's a slide here that shows how to bound the sum of sensitivities by roughly D for a large class of M estimators. So let me conclude. So we study active LP regression, in which we want to minimize the number of queries to the target vector. We give an algorithm based on sensitivity sampling with a key idea of partitioning labels of the B vector based if they're large or small with respect to the corresponding sensitivity. This gives an optimal dependence on D. We also achieve an optimal dependence on epsilon by this iteration argument. And we extend our ideas to active M estimator regression and bound the sum of sensitivities for such M estimators using this hashing argument I briefly mentioned. So that's all. Thanks.
Any further questions for David?
So I had a question about so the first constant factor you got where you didn't even need to look at B.
Oh yeah, that's right. Yeah.
Right, but how far can you?
Well, I mean, like the scores are just sensitivity sampling. I mean, when you sample by those scores, you read the corresponding entries at B.
Correct, exactly.
Yeah.
Yeah. But just to
Okay.
But if I so if I don't intuitively, but you've already sampled which rows of A you want to keep, right?
Yeah.
So
go ahead. Yeah.
Is that how far can you push that? If I don't want to look at the.
No, but I don't look at B either for
okay.
sampling for the 1 plus epsilon approximation.
Okay.
Yeah.
Okay.
So I mean, I'm just at the end of the day, it's just sampling by the Lewis weights of A. Yeah. I do get the corresponding entries of B, and then I solve that small problem. Yeah. But it is a good question how far you can push that simple triangle inequality argument. You can't get 1 plus epsilon because of the triangle inequality.
You think the improvement from D over epsilon squared to epsilon is basically refining the net being used?
You mean for P between 1 and 2?
I mean, this sort of a recursive argument that you showed.
Yeah, I mean, it's just in the analysis, right? It's like saying that if you had this...
True, but like in some sense, chaining should be tight, right?
Yeah, well, I mean, as I said, it's the way that we understand the proof of it, which is saying that if you had this 1 plus epsilon approximation, then the vectors are close, and then the chaining argument gives you a better sample complexity. And then, now you have a better approximation and so on. There might be a way of doing it more directly, yeah.
Okay.
I do want to mention, for P between 1 and 2, even in the non-active setting, it wasn't known how to compress a regression instance down to D over epsilon rows. Okay, so that's a result, that's potentially useful beyond active. It was only known how to get D over epsilon squared rows. So,
I see
so even if you could read the whole B vector and you wanted to...
The Lewis weight sampling does not get you D over epsilon.
Well, Lewis weight sampling with the B vector adjoined, which is the standard thing to do, would give you D over epsilon squared. And so even if you could read the whole B vector, we don't know how to get D over epsilon in any other way.
Thanks.
Sure.
Although weirdly, for when P is 2, it magically comes out of approximate matrix multiplication.
Yeah, when P is 2, everything is nice.
Yeah, when P is 2, the epsilon was already known, and it's immediate for a totally different reason, seemingly, which is odd.
Yeah.
All right, so let's think that in again.